In the construction of his theory of relativity, Einstein considers the rule of differentiation of determinants. Let me write it down and then let's try to motivate it. The differential of the determinant g of the metric tensor can be proved to be equal to g mu nu g differential of g mu nu. And he also says that this is equal to minus g mu nu with the lower indices times determinant g times differential of g mu nu with upper indices. This second equality is quite easy to verify because we can start from this identity g mu nu times g mu prime nu. This is equal to the Kronecker delta mu prime mu. But now if we sum over mu prime and mu, so if we contract the indices mu and mu prime, we get g mu nu, g mu nu, and this gives us delta mu mu, which is equal to 4. So if we take the differential from here, differential of this expression, we get g mu nu d g mu nu equal to minus g mu nu with lower indices, differential of g mu nu with upper indices. And therefore, it's easy to verify that if this first equality is true, then the second equality will also be true because of what we have just done here. But now let's try to dig deeper into this formula. Let's try to prove this formula. Now, the rule of differentiation of determinants can be obtained in this way. For example, first, let's assume that we are in a frame where the matrix or the tensor g mu nu is diagonal. So in this case, we will denote g with the tilde like this to denote that we are in a frame where g mu nu is diagonal. So also remember that the determinant of g tilde, which I will just denote like this, g tilde is equal to the determinant of the matrix g mu nu for basic rules in linear algebra, because the transformation which transforms the matrix g mu nu to the matrix g tilde mu nu is of this kind. We have some matrix lambda inverse mu alpha g alpha gamma multiplied by lambda gamma lower nu. This is equal to g tilde mu nu. We have a transformation like this which also works with the upper indices here and here. So it's the same if we consider the upper indices, because if we take the inverse of this transformation, we can also get something similar. For example, we can write it down like this: lambda inverse mu sigma g sigma tau lambda tau nu equal to g tilde mu nu with upper indices. And in this case, this matrix here represents the inverse of this matrix here. And similarly, this matrix here represents the inverse of this matrix here. It is quite easy to derive the second one from the first one. You simply take the inverse on both sides. And when you take the inverse of the left-hand side here, you will get that the inverse of a product of matrices is equal to the product of the inverse matrices, but they are multiplied in reverse order. So here from the left, I will start from the inverse of this matrix here. Then in the middle, I will have the inverse of this one, and on the right here, I will have the inverse of this one. So it's quite easy to notice this. But now let's work in the frame where g is equal to g tilde. So g is diagonal. Remember that g tilde is diagonal. And let's consider the ratio between dg and g. So the differential of the determinant of the matrix g tilde or g, because the determinant is the same. If you take the determinant here on both sides, you will get the determinant of g is equal to the determinant of g tilde, because here we have the product of the determinants when I take the determinant of this, and the determinant of the inverse of lambda is equal to 1 over the determinant of lambda. So they will get cancelled and I will be left with only the determinant of g. So the determinant of g will be equal to the determinant of g tilde. Now if we consider dg over g, this is equal to the differential of g tilde 1 1, g tilde 2 2, G tilde 3 3, G tilde 4 4 divided by G tilde 1 1, G tilde 2 2, G tilde 3 3, G tilde 4 4. And this is obviously equal to dg tilde 1 1 divided by G tilde 1 1 plus differential of G tilde 2 2 divided by G tilde 2 2 plus differential of G tilde 3 3 divided by G tilde 3 3 plus differential of G tilde 4 4 over G tilde 4 4. And this is equal to, now since G tilde is diagonal, its element G tilde 1 1 is equal to 1 over the element G tilde 1 1 with upper indices. Now this equality here is obvious from the fact that if we want to consider the inverse of a diagonal matrix, we simply have to invert to consider the reciprocal of each term on the diagonal. So we can rewrite this also as G tilde 1 1 differential of G tilde 1 1 plus G tilde 2 2 differential of G tilde 2 2 plus G 3 3 differential of G tilde 3 3 plus G tilde 4 4 differential of G tilde 4 4. And now in this frame of reference we can write G tilde mu nu differential of G tilde mu nu. Now we want to go to a frame where G tilde is not diagonal, so we will consider this transformation G mu nu equal to lambda inverse, and here we have the indices mu sigma times G sigma tau lambda tau nu, and also we consider the transformation G tilde mu nu equal to, we have the same matrix lambda inverse, and this is due to what I have said earlier, because when you take the inverse of that relation, you will get something like this. G tilde mu nu is equal to lambda inverse mu alpha G alpha gamma lambda gamma nu. Now if we go to a frame where G is not diagonal anymore, we know that the determinant is still the same, it doesn't change. So this part of the expression remains unchanged, but this is equal to this expression here, written like this. It means that this product here should also be independent of the frame of reference. So we must be able to write this as G mu nu d G mu nu in the new frame of reference. But we can also use these transformations here and here to derive this equality here, and therefore the rule of differentiation of determinants. Since the matrix G alpha gamma is symmetric, we can also use a transformation lambda which is orthogonal. So this inverse here can also be replaced with a transpose because of linear algebra, which tells us that if we consider a symmetric matrix, we can always find a transformation that in this case is called lambda, such that if I multiply the transpose of lambda by the matrix itself by lambda, we find a diagonal matrix. This transformation is true at some point P, because G in general will depend on a point P, it depends on the coordinates x mu, right? So at each point of space-time, I will have a different matrix lambda. Now let's rewrite this product by using these two formulae, this one and this one, in here. So G tilde mu nu can be written as lambda transpose mu sigma, where this first index here represents the row index, whereas this second index represents the column index. This is why I'm writing these indices in this manner. I'm not writing mu sigma like this, with sigma just below mu. I'm just trying to differentiate between mu and sigma. One is the row index and the other one is the column index. That's it. Then I have G sigma tau lambda tau nu and then I multiply by the differential of g tilde. Now, when I consider the differential, I'm changing just by a small amount the coordinates. So I'm moving from some point P to the neighborhood of the point P. And for the differential of dg tilde, I can replace this expression, lambda transpose mu alpha. Then I have the differential of g alpha gamma multiplied by lambda gamma nu. I can replace this expression for the differential of g tilde because this matrix lambda is constant. That's the transformation at point P, does not depend on the coordinates. Now I can rewrite this expression in this manner. I can put this term together with this term, and lambda transpose mu sigma here can be written as lambda sigma mu. I just change the order of these two indices and I remove this transpose because it will be the matrix itself, lambda sigma mu, and then I multiply by this, which is lambda transpose mu alpha, and then I will have g sigma tau differential g alpha gamma, and in here I'm going to multiply this matrix by this matrix because in here I can sum over nu. In here I'm summing first over mu, whereas here I am just thinking as if I am summing over nu first. So in this case I can rewrite that as lambda tau nu, which multiplies this matrix, and I can rewrite that matrix as lambda transpose nu gamma. But now, since lambda is an orthogonal matrix, this product will give me delta alpha sigma, the Kronecker delta, which is the identity matrix, whereas this one will give me delta gamma tau, and therefore now I can write this as, if I multiply g sigma tau by delta alpha sigma, so I'm summing over sigma, that will be g alpha tau, and here I have the differential of g alpha gamma, and here I have the Kronecker delta gamma tau, and therefore here I have g alpha tau with lower indices. But now we have just proved exactly what we wanted to prove, that this equality holds true, and therefore this is also equal to dg over g, and we have derived the formula that Einstein takes for granted, which is differential of g equal to g mu nu g differential of g mu nu. And remember that this is also equal to minus g mu nu with lower indices, g differential of g mu nu with upper indices.